Okay, in this lecture, we're going to talk about the work of a point charge distribution, which basically means we're going to try to understand how you can store energy by forcing charges together, or I should say, pulling them apart if they want to be together. Okay, but basically, we're trying to figure out how much energy you can store by putting charge where it would not naturally be. Okay, so let's think about this in terms of bringing together charges one by one. Okay, so we're going to calculate the work required to bring together a bunch of charges. Okay, one by one. We are going to bring them from infinity. So we're going to assume the potential where they start is 0. Okay, where the potential at infinity equals 0 to some radial distance. Okay, so we can calculate the work just by this formula here, Q times V times that radial distance. Okay, so let's think about this again, charge by charge. So we got our first charge here. We're going to call that guy Q1. Okay, this one is free because there's no E to fight against, okay? There's no electric field to fight. Okay, so if I want to move a charged object around and the only electric field it's generating is its own, it's not going to feel any force from another charge. All right, so that first one is free. We'll make this fun, do different colors. Okay, let's do the next one. So now I've got Q1 here, and I'm going to bring in from infinity another Q2, where the distance between them is going to be R12. Okay, in this case, I do have to do a little bit of work because I already have the electric field present from that first charge I moved into the space. Okay, so now the amount of work I need to do is Q2 times the potential that was generated from that first electric field. And so that I'm going to get 1 over 4 pi epsilon naught, and that's going to be Q1 because it's the potential from that first charge. And the potential that our second charge is going to feel at that particular radial distance is going to depend on Q1 divided by that actual distance from the first charge. Okay, so that's our first charge that we're dragging in. We're going to do another one now. So here's Q1, Q2 will still down there. This is still R12. But now we're going to add another charge here that I'm going to pull in from infinity. And that's Q3. Q3 is got this distance from our first charge, but we also have to worry about the electric field now of the second charge, which is chilling there when we pull in Q3. Okay, so I need to worry about that distance as well. So now the work done to pull in this third charge is going to be equal to the magnitude of the third charge, again, times the potential that was present when we were pulling it in due to the other two charges. We can use the principle of superposition here. So I can treat each of the original charges, the potential of each separately, and just add them together. Okay, so that's going to be the potential at this object's location due to this charge, and then I've got to add the potential at this object's location due to this charge. So that's going to give me another term. Okay, and I could do this a whole bunch, but let's end it there and see if we can see a pattern. So for this particular situation, the work total to assemble this charge configuration, I didn't actually write this is the free one, is going to be equal to the work done to bring that first charge in, which was 0, plus the work done to bring the second charge in, which was not 0, plus the work done to bring the third charge in. Okay, and when I add all of that up, I'm going to pull out this common factor of 1 over 4 pi epsilon naught, and I'm going to get a Q1 times Q2 for the first term over R12. The second term, I'm going to get a Q1 times Q3 over R13. And then the third term, I'm going to get a Q2 times Q3 over R23. Okay, and again, that's just from distributing this Q through here and this one through here and here, and then I'm adding that together. Okay, so if I look at that for a moment, I'm going to copy and paste this onto the next slide. You should see a pattern developing. So I can write out a larger rule that will generalize this for any number of charges. Okay, so let's go ahead and stare at it for a second and figure out how we can do that. Well, we've got pairs of charges here, 1 and 2, and then we always have the distance between them. So pairs, distance, distance. Okay, so maybe I could calculate the work total as that constant out front, but now I'm going to sum over each pair of charges. So I'm going to go from I equals 1 to n, the number of charges, and then I can do over j, but I don't want j to be equal to I because I don't do any, there's never going to be a term here, right, that's like Q1, R11, right? So I can do that one with n. And also this symbol here is to say I don't ever want to also add 2 of these. So for example, with this one, I've got a Q1 times Q2 over R12. I don't also need a Q2 times Q1 over R21. That would be this term counted twice, okay? So let me rewrite this out. This is a Qi, Qj over Rij, and then the notes are I is never equal to j, right? And then I don't want to double count. Okay, so essentially I don't want Q1, Q2, R12, and Q2, Q1, R21. Okay, that'd be counting the same thing twice. All right, but I can double count on purpose. Fancy physics here. And then divide by 2. So that's actually what we're going to do. Okay, so I am going to allow this double counting, but I'm going to divide the total amount of work then by 2. Okay, so that simplifies the formula in terms of these sums here, but I'm going to get this 1/2 out in front. And now I can just write this as the sum from I equals 1 to n, and then the sum over j's, but j cannot still be equal to I. And again, same deal here. This is Qi, and this is Qj, and this is Rij. Okay, so we did all this because we're going to simplify it even more. Okay, I'm going to rewrite that one more time just because I love writing this stuff down. But now I'm going to simplify it so you can see a particular relationship in there. And I'm going to pull this one over 4 pi epsilon naught into this inner sum, which I can do because it's just a constant. And I pulled the q sub I out. Okay, and everything else is going to stay, make that square bracket in here. Okay, so what I want you guys to notice here is that this is just calculating the potential of a bunch of charges. Okay, so this is the superposition of the potential of a bunch of point charges, okay? Which is to say that I can simplify this even more and say, oh, if I want to pull in some charge, I just have to sum the magnitude of that charge times the potential at that charge's location due to all the other charges, okay? And I'll do an example because I found this a little confusing the first time I learned about it. So I'm going to do an example to show you what that looks like. All right, so this is one of the problems in the book, but we will do it as an example. Okay, so we've got a charge configuration where we've got 2 negative charges on some corners, and then we got a positive charge here. And we are going to move this positive charge to the other corner. Okay, so I also know that this is a square and the sides here are equal to A. They have a length of A. Okay, so basically what I'm trying to do is I'm trying to find the work to add our plus Q to the charge configuration, or to the corner. That's fine. Okay. All right. So to calculate the work, I'm going to take that Q, and let me make that clear. That's our Q that we're moving. Okay. And I'm going to multiply it by the potential of all the other charges. Okay. So this is the total potential at the final location of Q. And by the way, we're moving this Q out from infinity, which means we don't have to worry about where it started, or the potential where it started. Okay, so let's do that. We've got our Q out here, and then I just have to figure out what the potential is at our point Q here due to these other charges. This one and this one are pretty easy. We just get negative Q over 4 pi epsilon naught. There's a 1 over A here, and then you get another one of those, because that is the distance. Okay, this one is just slightly trickier. We got to use the Pythagorean theorem, but for that it ends up being a positive Q, because that charge is positive, over 4 pi epsilon naught times 1 over the square root of 2a. Okay. All right. So I can simplify that just a little bit, and you end up getting Q squared over 4 pi epsilon naught. And I don't really feel like simplifying this too much because I'm mostly just trying to show you how to do it. Something like that is fine. Okay. And now let's do a different type of situation. Okay, so this is just the work that you need to move this charge to the corner. That's going to be different. Okay, this is our part 1. That's going to be different than part 2 of this problem, which is to find the work to assemble the whole charge distribution. Okay, in that case, we want to use this formula that I just talked about, this 1/2 times the sum, in this case of I1 to 4, because there's only 4 charges, Q sub I times the potential at each position of charge. So basically what we're going to do here is we're going to take the product of the charge and then the potential at each location of that charge due to all the other charges. Okay, so let me just write that. This right here is the potential and charge at each location. Okay, and I have to consider, again, when I'm doing this at each location, I have to consider all of the other charges. So this ends up being a little bit longer. I get a 1/2 out here still. I'm going to pull that 1 over 4 pi epsilon naught common factor out. Okay, and then let's do it 1 by 1 here. So I'm going to label this as 1 and 2 and 3 and 4. Okay, so for the first one, I'm going to get basically what I just found up here. Okay, I will get Q squared and then times all this stuff. Okay, so that is the same as, right? This was what we just did, the charge times the potential at that point due to all the other charges. Okay, so that is what I'm going to get at for that first part of my sum. Okay, if I look down here, this third part, it's actually identical. It's just symmetric. So the term is going to look just the same. So I actually get two of those identical terms. Over the square root of 2a. Okay, so this would be a third term. Okay, and then the same thing, if I can figure out what the potential is at one of these guys, it's going to be the same as the potential here, right? Because this guy is it'd be this charge, this negative Q, times the potential due to these three charges, which is identical to what the potential would be here due to these three charges. Okay, so I'm just going to skip it a little bit, and then I'm going to get 2, a factor of 2 times this other term. And that's going to look just a little bit different because of the differences in the signs of the charges. Okay, and hopefully I didn't make a sign error there. But this is 2 and 4, okay. And then again, you can do a lot of simplifying, okay. When you simplify this down, I'll let you guys do that if you want. You get 1 over 4 pi epsilon naught. You can get 1 over, pull a factor of 1 over a out, and then just a bunch of funky numbers here. And you can simplify that even more by calculating what that number is, but I don't want to do it. But the point is that you you calculate a different amount of work just to pull in this one charge into a already set charge configuration than you do to actually assemble the whole charge configuration. Okay, and of course now we can think about this work as being that we did to assemble this charge distribution as being the amount of energy that's stored in this charge distribution. We could store that energy just like we store energy in a battery and then release it and use it to do work.